So our next type of variation is known as joint variation. To describe two different direct variations in the same statement, the word jointly is used. The variable z varies jointly as the variables x and y, or we say z is jointly proportional to x and y if z equals kxy for some constant k. Notice that in this case, we are going to have a relationship between three different variables, x, y, and z. All right, z is dependent on x and y. So I have one dependent variable, two independent variables that we are going to plug in. And still I have this constant of proportionality k. And again, when you see joint variation, this is like double direct variation, all right? All multiplication, k times x times y. The cost of insulating a ceiling of a house varies jointly as the thickness of the insulation and the area of the ceiling. It costs $175 to insulate a 2,100 square foot ceiling with insulation that is 4 inches thick. Find a mathematical model that gives the cost as a function of the area and thickness. So let's begin, as always, by identifying our variables. What is our dependent variable? Well, that is going to be our cost. Let's label that as C. And our cost is dependent on two separate things. It's dependent on the area that we have to insulate, let's call that A, and the thickness of the insulation that we choose to use. All right. Now that we have identified our variables, let's come up with our relationship. Because this is joint variation, we are going to have C is equal to K times A times T. All right, it varies jointly. The cost varies jointly as the thickness and the area of the ceiling. Thickness of the insulation and the area of the ceiling. So to finish our model, we must solve for the constant K. And to do so, that means we must plug in our given information. We start off by plugging in $175 for C, $2,100 for A, and 4 for T. Solving for K, doing out the algebra, gives us K is equal to 1 over 48. And once we have that constant of variation to come up with our model, we just plug it back into our expression. C is equal to 1 over 48 times A times T. This model right here would give us the cost for any area and any thickness of insulation that we want to plug in. All right, so if we change our mind on how much ceiling we want to insulate or on the thickness that we want to use, we can get an idea of what it is going to cost. All right, let's do another example. The load that a 20-foot horizontal beam can safely support varies jointly as the width of the beam and the square of the height of the beam. Let's read that one more time carefully. The load, okay, that's going to be our dependent variable right there, the load, can safely support varies jointly, all right, so I'm going to be multiplying two different things, as the width of the beam and the square of the height of the beam. Notice the word square here, all right? What does that mean? Well, let's see if we can't come up with our model. All right, one, we said our dependent variable is going to be the load. Let's call that L. What is the load that we can safely support depend on? It depends on the width of the beam, we'll call that W, and the square of the height of the beam. The height, let's call that H. Now, we have joint variation between our width and the square of the height of the beam. That gives us L is equal to K times W times H squared. Notice we squared the height. Why did we square the height? Because in the problem it says that it varies jointly as the width and the square of the height. Again, read those problems carefully and underline any important information. Okay, so let's come up with our model. We have L is equal to KWH squared. To finish this model, we must solve for our constant of proportionality, K, and we can do so by plugging in the given information. We know that our beam can support 200 pounds with a beam that is a width of 2 inches and a height of 6 inches. We have 200 is equal to k times 2 times 6 squared. All right. Well, 6 squared, that's 36 times 2 would be 72. 200 over 72, that reduces into 25 over 9. There we have our constant k. And now that we have our constant k, we have our mathematical model. L is equal to 25 over 9 WH squared. Once the model has been generated, plug in the width and the height in question to determine our new load. Well, how many pounds can a beam of the same length and material support if it's 4 inches wide and 4 inches tall? L is equal to 25 over 9 times 4 squared. Plugging that value into our calculators gives us 1600 over 9, which is approximately 178 pounds. Again, don't forget your units with your answers to word problems. That will cost you points. Include units to your answers. All right, and our final type of variation, all right, is combined variation. Combined variation is when we see direct and inverse and maybe some joint variation occurring at the exact same time. All right, so we have multiple variables that are going to be related. So it's important that we are able to read the problem carefully to set up our expression. Here's our example. The load that a horizontal beam can safely support varies jointly, all right, that's a key word right there, jointly, as the width of the beam and the square of the height of the beam, okay, and inversely is telling us to divide, right? Inverse variation means divide, as the length of the beam. If a 12-foot beam with a width of 4 inches and a height of 8 inches safely supports 800 pounds, how many pounds can a beam of the same material support if it is 16 feet long and has a width of 2.5 inches and a height of 6 inches? So let's identify all of our variables here. Our dependent variable is going to be our load, right? The amount of weight that our beam can safely support. Let's call that L. And what is it related to? What is it dependent on? L depends on the width of the beam, call that W. The square of the height of the beam, we'll call the height H. And inversely as the length of the beam, let's call that lowercase l. So I've got load is capital L, length is lowercase l. Don't make them the same letter. You will confuse yourself. Okay, let's now come up with our expression. We have capital L, the load, is equal to K times W times H squared. That's jointly as the width and the square of the height divided by L. That's inversely as the length of the beam. So to come up with our model now, we must solve for our constant K, right? That's what we've been doing this whole time. We can do that by plugging in the given information. We know that our beam can support 800 pounds, that's our load, when the width is 4 inches, the height is 8 inches, and the length is 12 feet. We plug those values in, which allows us to solve for K. Solving for K, we get 37.5. Now we have our model. L is equal to 37.5 WH squared. And once we have our model, we can answer the next part of the question. How many pounds can a beam of the same material support if it is 16 feet long? That means we're plugging in 16 for little l. The width is 2.5 inches, that's W, and a height of 6 inches. We get L is equal to 37.5 times 2.5 times 6 squared, all of that divided by 16. And again, if we want to get an exact answer, we plug that into our calculator, we hit the math frac button, that gives us 3,375 over 16, which is approximately 211 pounds for our load. All right, so there you have it. Examples of joint and combined variation. That's it for Chapter 1.